Ladies and gentlemen, welcome to Seoul, Korea. And it's time to begin the plenary lecture, the very first plenary lecture for the title of Does the Catalyst Allow Driving a Car, as well as having a clean air, by Roel Prins. Probably Professor Batch will introduce about speakers. Could you speak about it?
Good afternoon, everybody. It's a pleasure for me to introduce Roel Prins. Many people will know him already, but he started his research career in 1967, where he did his PhD in physical chemistry at the University of Amsterdam. There he joined the Shell laboratories in Amsterdam, working in a group of Wolfgang Sackler. He's moved from Shell in Amsterdam to Shell in the United States and came back to Europe in 1977 as a professor at the Technical University in Eindhoven. He stayed there for almost 10 years, during which he had a sabbatical in California with Gabor Sommerjai and Alex Bell. He returned then to move to ETH in Zurich in 1987 and remained there again for almost 20 years until 2006, when he formally retired from ETH. But like many eminent scientists, retirement is just a word that appears in a dictionary and doesn't actually mean anything in real life. And of course he has continued to be very active in research. He's an editor of the Journal of Catalysis. He's a foreign member of the Royal Dutch Academy of Sciences, and he is an honorary professor in 3 universities in China, in Dalian, Taiyuan, and Chengdu. Ladies and gentlemen, it's a great pleasure to invite Roel Prins to give his plenary lecture to open this conference.
Thank you very much, Mr. Chairman. Thank you very much to the organizing committee, Professor Moon, Professor Wu. It's an honor to be here, and I'm happy to tell you something about a subject of hydrodesulfurization, the removal of sulfur from fuels, which is related to the question you see already on the screen. And some of you may already ask yourself the question, will I be going to say yes, or will I be going to say no at 6 o'clock? Will you be driving a car at 6 o'clock or after 6 o'clock or not? Well, this sometimes depends in Europe and from which part you come. It's Sunday, so it then depends. If you are Catholic, you would say yes, and if you are Protestant, you may say no. But let's go to the next slide. How do I do that? Do I click here? Yes. Well, here you see the problem that is facing mankind, and this is very well known, that it is that after World War II, there is an explosion of the consumption of any type of energy. And in red, I've indicated fuel, which is going to be a fuel for your car, be it a gasoline-driven car or a diesel-driven car. And you see it's still increasing. Now, on top of that, the world population is increasing. So you see that, do you see the mouse here? Yes. So we are now around 2000 and something, so we are having 6 billion people on planet Earth, and in a little less than 50 years we are here, we will have 9 billion. Just yesterday I read in a Japanese paper that in 2012 they expected 7.5, so even this line is under the prediction that was in the paper yesterday, be it slightly. So let's say we have another 50% more people on Earth in another 40, 50 years. Now, all of you love driving a car. So I'm sure that also the future generations and the people who are now young and will be mature by 2050 will also love a car. And that means with also the improvement of the living standards in many, many countries of the world, there will be many, many cars in the years to come. And you can see that in this picture, which is just giving the difference between 1950 and 1997, let's say 1950 and the year 2000. You see that even the US of A in blue is still doubling. Of course, Europe is going up faster, but hasn't reached the level of the US number of cars yet, but you see the strong increase because Europe started at a lower level. And you see something similar for one country I took out of Asia, and that is in this case India. And you see that they, of course, started around 1950 at a very low level, but are going up fast. And of course, they have this delay with Europe and a further delay with the US of A, but they will one day, hopefully for them, for everybody, drive a car as well. So one car a family at least. And I'll give you another Asian example, which I took from the web. This is a picture, 3 pictures of Beijing I will show you, with a difference of 10 years each. So 1980, in China, everybody was having a bicycle. And if you didn't go by bicycle, you were going by bus. 10 years later, you still see a lot of bicycles, you still see quite a few buses, but you see the first passenger cars coming. And then, a few years ago, you just see passenger cars and buses, and the bicycles in certain cities of China are going to disappear. And so you see it's happening all over the world, and especially, of course, in the countries that are fast developing, and there will be many, many more countries like this. What does this mean? Let's do a back-of-the-envelope calculation. I assume today that there are 300 million people each in 3 parts of the world consuming a lot of fuel. That is the US of A, Europe, and Asia together. They are roughly each 300 million people. So 3 times 300 million is rounded off, 1 billion people. Let's say each of you drives 30 kilometers to work or whatever per day per person, and let's assume you have a car which has an efficiency of 10 kilometers to the liter, so you drive 3 liters per day per person. Times 1 billion people, that gives 3 times 10 to the 9th liter per day, which is 3 million tons a day. Now, what does this mean for air pollution? This by itself wouldn't make a big problem as long as we still have oil. I will not touch upon the fact today if there will be oil forever. I will now start touching upon the fact that oil isn't as pure as we would love it to be. Oil has sulfur in it, and we'll see in a minute which kind of molecules. Now, an average oil can have between 0.1% up to a few percent. So let's say 1% sulfur, now 3 million tons a day of oil, gives 1% sulfur, gives 30,000 tons of pure sulfur per day. So that is what's happening today. There's 30,000 tons sulfur produced every day on Earth. Now, of course, we don't want this to go into the air as sulfur dioxide, because that would be not very nice in the urban areas, and it would be impossible. So legislation has already demanded in most countries of the world that we must do something. And what do? Well, the refinery does it for you. Here you see a schematic diagram of a refinery. You see on the left-hand side that oil is coming in. Where's the mouse? Here. Yeah. And you see a distillation tower, which means you distill it in low boiling point fractions, like which is called naphtha, kerosene, and then heavier is gas oil. And in the end, you have the atmospheric residue and the vacuum gas oil. Then they all go through something which is violet-like, which is, at the bottom you see the word, it's hydrotreaters. They remove sulfur and nitrogen, but mainly the sulfur. And you see that all the streams are cleaned, because in the end, and now we are going to the right, you see the word gasoline. So naphtha is going to gasoline, and kerosene is going to kerosene, and gas oil is going to diesel, and that is by straight distillation and cleaning up. But more than 50% normally of the oil is in the bottom fractions. And of course, we don't want to waste that. In the old days, we would use it as fuel oil, but today we want to make a product from it which has more value, so that is gasoline and diesel. And because mankind wants to drive a car forever, there's a good outlet for it. So what you have to do is those big molecules which are in the atmospheric residue and vacuum gas oil fraction, those very long molecules, you have to cut them into pieces so that they are smaller, so that they become a molecule in the boiling range of a naphtha, which goes to gasoline, or a gas oil, which goes to diesel. And that's what you see in this picture as well. You see at the bottom that here your vacuum gas oil is going through a hydrotreater, then to cat cracking, catalytic cracking. I'll come back to it. Now, often in a refinery, before the cat cracking, there is no hydrotreating. Many countries, especially in Asia, don't have that. I'll come back to that, what that means for the sulfur. Because it means that this part, which is cracked, and is now, you see the blue line, is going to the gasoline, or also partly to the diesel fraction, is now a gasoline and a diesel, which still has this 1 or 2% of sulfur in it. Now here you see the specification. I've just taken the European ones, but many countries have specifications like this, like Japan, Korea, the US. So a straight run oil, when you take those fuel fractions, they may have like 0.5% up to 3% of sulfur, as I already mentioned. And in ppms, that's 5,000 to 30,000. There is also nitrogen in there, much less, normally a factor of 10 or more or less. Then the European Union in the year 96 had new legislation demanding that we go down to 500 ppm, and we had to, and we did. Then in the year 2005, we went down to 50, and now next year and the year thereafter, depending on which country, we have to go down to 10 or 15 ppm. So you see that over the years, we have gone, let's say, in last century, 1980, no legislation, then it was 1,000, then it was 550, 10, almost zero. I've also indicated the nitrogen level, but there is no legislation. This is only to indicate that these two feeds, these two molecules, nitrogen-containing and sulfur-containing molecules, are always together in the feed. And although I will not address it today, the nitrogen-containing are very difficult, and they hurt the removal of sulfur because they absorb more stronger, so there is inhibition. And that means you better also remove the nitrogen, because otherwise it will not allow you to remove the sulfur. And that means in the bottom you see industrial conditions, it's always a mixed feed, you have to do both. Now at the top of this slide, I've indicated another problem. There is still oil, and there is still a lot of oil in the world, but the good quality oils are gone or are going out. That means in the future we have to live off oils of less and less quality. In other words, the oil becomes dirtier, and for the subject of today, there will be more and more sulfur in it. However, at the same time, as you see here, the legislation, the countries, you as a citizen, you demand clean air. It's not your government, it's you. You are the government, you are the people, you are the democracy. So you demand clean air for you, for your children, for your grandchildren, for a world to come. This is what we call sustainability. So here is the problem. The oil becomes dirtier, and our demands become more stringent. So what do we do? And here you see the problem at the moment. We are going to go there in the right direction, but we aren't there yet. I've indicated in the world map 3 colors. In green, let's call them the good guys at the moment. They have legislation which is stringent, or they have it next year or in the year 2010. So low sulfur level in the fuel required, and all refineries must do that. Then you have the yellow countries, the yellow-colored countries, which have it less stringent. They are like Europe in 96. They may be at a level of 500, or they may be at a level of 100, but they're far away yet from the level of 10 ppm. And some of them have not indicated yet when they will go to 10 or 20 ppm, to a real low level. And then in addition, you have the countries who have no legislation yet, no standards. And you see that, funny enough, some of the big oil-producing countries are among them. Anyway, you see that there's a lot to do for the world, and you see especially in Asia, where of course the population is now going to drive more and more cars. You can see that any day when you come from year to Asia, you see the number of cars exploding. And then think about the population. There is, like I said, something like 300 million people in the US, something like 300 million people in Europe. But there is 1,300 in China, and there is 1 billion people in India, and there is something similar in Indonesia, and so on, and so on, and so on. So they are, in the end, almost like a factor of 10 bigger in population than we are. And one day, we'll hope for them, if we all still can afford to drive a car, that they also drive a car. And you see that happen at the moment in Asia. So no doubt about it, these countries, which are now colored yellow, have to turn green. The sooner the better. Now, let's look a little bit more scientific to this problem. What does it mean when there is sulfur in a feed like gasoline, or in the naphtha, which is the precursor of the gasoline, or in the gas oil, which is the precursor of the diesel? At the top, you see 3 molecules. The standard molecule is called thiophene to the left. Where is the mouse? Here it is. And then when you put 2 benzene rings around it, you annulate it, you have the so-called dibenzothiophenone, or you can have that same molecule with methyl groups attached to it, and in this case they are very close to the sulfur, and those positions we call 4 and 6. So it's 4,6-dimethyl dibenzothiophenone. In the bottom I indicated some nitrogen-containing molecules. You have molecules with the nitrogen outside the ring, like an aniline, or the other 3 where the nitrogen is inside the ring, which is always the case in oil for the sulfur. Because sulfur outside the ring is easy to desulfurize, and geology has already done it for you. The oil is old, hundreds of thousands or millions of years, and then geology, heat has already done it for you, but the nitrogen-containing compounds are more robust, and therefore they have survived, even with the nitrogen outside like aniline. Now, there's 2 problems to remove sulfur from fuels, and the one is the naphtha problem, which is the gasoline, and the other one is the diesel. And let me spend a few words on the naphtha first. First of all, I already indicated that at least 50%, and sometimes 60 or 70% of the barrel of oil is, when you distill it in the refinery, is a heavy product. And that means it's very heavy, and it has to be cracked to make smaller molecules to make gasoline and diesel. So you have to crack it, for instance, by fluid catalytic cracking. And normally, or in most cases, there is no desulfurization in front of it. And the FCC itself can survive sulfur. So that's the easy way out, the cheap way out. So there is no desulfurization. And out of your FCC unit comes a product with sulfur. And normally this is the thiophene. So now you see at the top line, you see that naphtha, which is coming from the fluid catalytic cracking in the Western world, in Europe and the US, may be 35 in volume of the total amount which is going to the gasoline pool for the car. But that 35% has 90% of the sulfur. In China, as another example, where they heavily depend on the fluid catalytic cracking to make gasoline, because they have a much heavier oil in Daqing in China, and therefore they have less in the barrel which goes directly in the distillation to the gasoline, so most of it is indirectly through the cracking. And then they have 75, and that means 98% of the sulfur. So here you see the problem for a country like China. They really have to come up with a different type of technology that we in Europe and in the US have introduced, and also in Japan. Nevertheless, over the past 10 years, industry has come up with a solution. Now, what is the problem? You might say, okay, then you desulfurize. And there is technology there. I'll show you a little later how to do that. There is a problem, though. In present-day technology, we remove the sulfur by hydrogenating the molecule. We cut a sulfur carbon bond by adding hydrogen atoms to it. So we come in with hydrogen at elevated pressure with a catalyst. And so it's a hydrogenating type of a catalyst. Now the problem in the naphtha is, which comes out of the FCC, of the cracker, that in the process of cracking you have alkanes which go to alkenes, to olefins. Now an olefin has a double bond. Now a double bond is very easily hydrogenated. So if you would do the normal technology of hydrodesulfurization, you would hydrogenate the olefins to alkanes. Well, what is the problem? Well, the problem is that the olefins have a very high octane number, whereas the alkanes don't. They have a low octane number. So if you would do that, you would give away a lot of octane. And then you have to do something else in your refinery, which costs. And it's also bad for the environment because every step in the refinery means energy consumption, means CO2 formation. So the less, the better. So the aim of the game is keep your olefins and still get rid of your sulfur. And still we try it, the industry and academia has tried it, by the hydrogenating route. Is this possible? Well, I remember some 15 years ago when some companies came to me and asked me, what is your advice? It looked like it was impossible because in those days most companies were looking for the catalyst to do it. Until they found out that there is an engineering way out, and which is a very clever way. They realized that the thiophenes which are there are more in the heavy part of the naphtha, whereas the olefins are in the light part of the naphtha. So what is the trick? Well, easy enough for an engineer, for a chemical engineer, do a distillation. Split them in two. Don't do the desulfurization of the light fraction so that you don't lose your olefins, and do the desulfurization of the heavy fraction. You lose some olefins, but not many. And that is roughly the trick that they do. So the bottom two here, this one is splitting it, and this one is another trick. Also clever. If you have those olefins and you have the thiophenes, which is just this 5 ring with one sulfur atom, why don't you alkylate with the olefins, with an acid catalyst, your thiophene? And that's an easy step. Then you have, like you say in English, you catch thieves with thieves. So the olefins are catching the thiophene, making it into a bigger molecule, which is more heavy, so it has a higher boiling point, so the separation in boiling fraction is easier. And that is the Oates process, which you see here. So you take your naphtha, which contains olefins, together with thiophenes, you bring it through a reactor, the Oates reactor, there is an acid catalyst there, you do alkylation, now you have alkylated thiophenes, they have a higher boiling point, so in the bottom fraction of the separator, the distillation tower, they come out, and you don't need a big distillation tower here. And the light fraction, which is almost sulfur-free and has the remainder of the olefins, comes up, and you can then desulfurize the bottom fraction and combine them, and you have a nice naphtha. The other possibility is the prime G process. There are many others. I just give you a few examples. This is the Axen's French process, where they do the splitting first in a distillation tower, and then they bring in the bottom part, they bring through a catalyst and do a desulfurization. Well, a slight variation of this, even more sophisticated technology if you wish, so a real chemical engineering approach, is combine the distillation with the catalysis. So go to catalytic distillation, which of course, as we know, is becoming more and more en vogue. And here you see that you have a distillation tower filled with trays with catalyst on it. And in the bottom part of your tower, you have a different type of a catalyst than in the top. In the top, your light fraction goes through. This may have mercaptans only, and that's very easy to desulfurize. So all you need is a very, very mild catalyst. And in the bottom fraction, you take a more robust catalyst, which can crack the thiophene and ring open it and then remove the sulfur. Okay, so far so good. This is all I wanted to say about the naphtha. This is now technology which is in place. So as far as the gasoline problem, I think the technology is there and we should just apply it. Now I turn to the diesel. The diesel is more of a problem, and is also scientifically more of a problem because we haven't really understood every part of it. And so I want to give you some insight in what's going on in the field. Another reason is, of course, that the diesel is becoming in certain parts of the world more and more important. In the old days, we were driving a car only with gasoline. Now we understand that it's not so clever to only use gasoline as a fuel, but it's also clever to use the diesel because we get them in the refinery anyway. So instead of turning a diesel into a gasoline, splitting it down the middle and have two smaller molecules, which are then in the gasoline range, you may as well use the diesel molecule, the gasoline molecule, and use it directly. That's more efficient. You don't lose, you don't waste energy in the refinery. So as a total process, from start to end, that makes sense. So in Europe, you see that the diesel is making huge inroads and is almost like 50% of the vehicles on the road now. So I just remind you in this scheme again of the refinery, the gas oil in the middle, going to the diesel. And how is that done? Well, until now, the cheaper the better, so it's a classic engineering approach. You take a big steel vessel, you fill it with the catalyst and your feed, which is a vaporized fuel, in this case the gas oil, together with hydrogen at high pressure, something like 5 megapascal or something like that, let's say 50 bar, 30, 50 bar, 70 bar sometimes, temperatures like 300, 400 Celsius, and it flows through the catalyst bed and comes out at the bottom, and it's desulfurized, and the sulfur goes to H2S, hydrogen sulfide. Now, there is one problem with this, which makes it extremely difficult to use this kind of scheme in the future. And the reason is that the product, hydrogen sulfide, is a poison for the catalyst. I'll come back to it at the end of my lecture to come to explanations why. But let's just assume it's true for the moment, and it's really true. That means that in the bottom part of your bed of the reactor, there is a lot of H2S because you have removed the sulfur, you have made H2S, and this is a poison, so part of your bed is not working well as a good catalyst. So it would be clever to go to a so-called two-stage process, where in the first reactor you do it to a certain extent, then you do a gas separation, you remove the hydrogen sulfide from the gas coming out of reactor 1, and with the remainder you go to reactor 2 and you start all over again. And then of course you split it into parts, and both have less H2S at the bottom, and therefore you can do what we call deeper desulfurization. And that is the aim of the game, go deeper and deeper. Remember, we started at a legislation requirement like 1,000 ppm, then it became 500, then it was 100, and now, then it was 50, and now it's 10. So going from 100 to 10 is a factor of 10. And 10 in rate could also mean a reactor 10 times bigger. Or it means, in this case, because of the H2S poisoning, just take 2 reactors, but remove the H2S in the intermediate stage. So therefore, we call this two-stage. So many refineries have now gone to this two-stage type of principle, which of course is more expensive because you need 2 reactors, with a lot of extra lines and so on, and it's all high pressure. Now, for a chemist, what is the problem? The problem is here. I'll show you here the network of the hydrodesulfurization of dimethyl dibenzothiazine. I will not mention the 4,6 anymore because this is the most difficult molecule. So many of the colleagues, they use this kind of a molecule as a model molecule. And you see that it is a difficult network, a complex network. The molecule starts here, and there's 2 ways of removing the sulfur. The so-called direct desulfurization. You just cut this bond and you cut that bond, and you put hydrogen atoms on the sulfur from either side, then you have H2S, and you put a hydrogen atom at the carbon atoms, and then you have the biphenyl type of a molecule. Or you start hydrogenating the molecule, so you go to what I call tetrahydro dimethyl dibenzothiazine. So you see I have hydrogenated here 4 carbon atoms. You can go to full hydrogenation of 1 ring, then you have hexahydro, or you go to both rings hydrogenated, which is officially called dodeca, 12, or it's also called perhydro, totally hydrogenated. And now these molecules, after partial hydrogenation, can now break a CS bond, and then from here you get this, which is a cyclohexobenzyl. It's a cyclohexyl with a benzyl, and here it's a double cyclohexyl, so bicyclohexyl. And the reason is, as we originally thought, that a aliphatic CS bond, the carbon being part of an aliphatic ring, is weaker. I think anybody in the field, I've never seen anybody doubting this. So this was always quoted as one of the reasons when you go this hydrogenation route, that the more you hydrogenate, the weaker the CS bond is and the easier it is to break it. Now this idea of this network goes back already 30 years, as far as I'm concerned, and started with the group of Bruce Gates when he was still at Delaware, exactly 30 years ago now. And he came up with this scheme. He started with the original molecule. He saw a little bit of the tetrahydro, but none of the other intermediates. And of course, he saw the final products, the hydrocarbons. A few years later in France, Vrina and de Moor took this work up, and then in Japan there was a lot of work. I'm sorry, I can only mention a few here. The group of Kabe. Later, Mochida had a review in 98, and in the meantime, Girgis and Gates again, they had a nice review. It just gives you a flavor of the field. I just want to tell you that the idea about this scheme is not new. That was already there since, I would say, 30 years. Now, why is there a problem? Why is this molecule with the methyl group so difficult? Let's go back one step and let's look at the molecule without the methyl groups. I show you here catalytic results of my group with dibenzothiophenone, so the same molecule, 2 rings, sulfur hanging in between, no methyl groups. It's a nickel moly catalyst, 340 Celsius, 50 bars, and a little bit of H2S to make it mimic industrial conditions. Now what do you see? You see at the bottom here the network. Here is the original molecule in red. Here horizontal is the hydrogenation line, in blue the intermediates, and then down at the bottom line in black the hydrocarbons. Sulfur removed. This is what we want, remove the sulfur. Now what do you see? You see that when I start with dibenzothiophenone, no methyl groups, my major product is this. I do a direct desulfurization. This is, as you see here in the selectivity plot, like 75%. 3/4 goes this route. So that's nice. First of all, you only consume 2 hydrogen molecules, not more, like you do in the other route. And secondly, it goes fast, so it's nice. And you see some hydrogenation. The other 25% goes the horizontal route first, and then goes down, like you see here. I've indicated this molecule, which is this. This you can hardly see when you take nickel moly at this temperature. The only intermediate you see is tetrahydro, and several people, several colleagues have seen that. But under nickel moly conditions, it's very difficult to see the hexahydro or even the totally hydrogenated. Now let's now go to a molecule with the methyl groups, and here it is. Now the first thing you see is that the conversion is much less. Oh. Does it work? Doesn't work. So it's much less. What you can see is that the hydrogenation is, well, if you would overlay it with the previous slide, that is the same. So the hydrogenation route hasn't lost much. It's the direct desulfurization. It's this part which has lost almost everything. And you see that also in the selectivity. Now this totally aromatic molecule is only 20% instead of the 80-75%. And the other 2 are the remainder. Now you see also quite a bit of a fully hydrogenated molecule. So I've gone through mainly now, 80% now through the hydrogenation. If you look at the rates, the hydrogenation is still at the same rate, more or less. It's the direct desulfurization, this one, which has lost it. Why is that? Let's look at the catalyst, then we understand. The catalyst in industry and most of academic studies, they use alumina as a support, and they use molybdenum disulfide as the catalyst, promoted with either cobalt or nickel. Now the MOS2 is a sort of Belgian structure. It's like a Belgian waffle. It is 2 layers of sulfur with the marmalade in between. And the marmalade is the molybdenum, and that's what is doing the catalysis. Now because of the top and bottom layer are totally sulfur and are not capable of doing the catalysis, it is only the edges. As you see here, some atoms, and here when you have a top view, then you see here some molybdenum atoms, but here on this side, the molybdenum are hidden behind sulfur. So it's only, in this case, the so-called molybdenum edges, which are expected to do the work. Now, why is this now suddenly a problem for the one molecule with and the other molecule without those methyl groups? Let's take a look. If I put my MOS2 slab vertical, then, and I put the layer with the molybdenum atoms at the top, here it is in blue-gray, then I can have 2 types of approaches. of my molecule. The one which we call sigma bonding and the other pi bonding. The one is where the sulfur of the dibenzothiophenone approaches a molybdenum and is going to make a bond. Because of that bond, this will become a strong bond and you get a molybdenum-sulfur bond, and then the carbon-sulfur bond is breaking, and you replace those bonds by hydrogen atoms, and you have what we called the direct desulfurization. And here you see it rotated 90 degrees, no problem. The other mode is the molecule flat on top of this MO2 slab. And you see this is also possible. And of course, the pi electrons, which are perpendicular to the dibenzothiophenone molecule, are now sticking towards the molybdenum. So this makes for easy hydrogenation. So it's all very understandable. Now what happens now if I add methyl groups? And you see it. You see that my methyl groups, they stick out in space further than the sulfur lone pairs do. And that means it is almost impossible to make a bond now between this molybdenum atom and the sulfur, because at the same time, these methyl groups are stuck on the neighbors of that one single molybdenum, which are other molybdenums, and I can't approach the surface close enough. So the sigma bonding is almost lost if you have a site like this. It's only at corner sites, and there are very few of them, where you can hang your methyl groups around the corner, as it were, and can do the job. But for the majority of the molybdenums, you can't do that. Now, what's happening? Can somebody help me? Great, thank you. So here you see this molecule with the methyl groups, and you see that when I have the flat absorption, where is the mouse now? Here it is. You see that now in the flat absorption, the methyl groups are sticking a little bit out, but that's not a steric hindrance. So actually, in the pi mode, there is no loss. Actually, I tell you, the methyl groups are electron donating, as any organic chemist knows from freshman chemistry. And that means the basicity of my dibenzothiophenone is increased by the electron donation. And since the molybdenum side, of course, is a Lewis acid side, you have a stronger acid-base type of interaction when you have alkyl groups on the dibenzothiophenone. So actually, when you really do the kinetics, you see that the hydrogenation is even improved. It's strengthened. So you don't lose at all, you win. So this is the explanation, that when you have those alkyl groups around the sulfur, there is this steric hindrance, and you lose this very nice direct desulfurization, and you live off the hydrogenation. So this is why this catalyst must be a good hydrogenation catalyst. Okay, now over the past years, we tried to look a little deeper in this. And so we have gone down in temperature, and we have used a catalyst like molybdenum sulfide instead of nickel moly, because now reactions are slower. And now you see a lot of in blue, the tetrahydro and the hexahydro. And you see it in this scheme, of course. I can find the mouse again, here it is. So the first step is making a tetrahydro, then you make a hexahydro, and we can look at that. It would be even nicer to not start here in red, but start here with the tetrahydro and the hexahydro, because my scheme is still very complex. And as any engineer or even a chemist knows, in such complex kinetics, it's very dangerous to come up with rate constant of reaction constants which are far away from the starting point. So we set out to make those tetrahydro and hexahydro compounds. And at the top, you see a recipe that we published in 2006, which I cannot recommend anymore. It looks very simple. You start with your molecule, you hydrogenate it, and you go further, and you seem to have the tetrahydro and the hexahydro. In reality, you make a soup, because you get everything at once. Not only this, but also the desulfurization, so you lose the sulfur, you get the hydrocarbons. And to circumvent that, you have to go at low conversion, which means recycle, and so on and so on. So actually, this is about 2 months of work of one postdoc and 2 students to do very big chromatographic columns, like 30 centimeters wide. So that's not a good recipe. So we came up recently with a new recipe, which we published in an organic journal, which looks more complex, yes, but it's a very clean recipe, and all the molecules which are the starting points are commercially available. So in the end, you have a very high efficiency to the tetrahydro. Now the good thing is when you start at the tetrahydro, and this is now the trick, when you start here, you can go either way. You can aromatize this and go here with good organic tricks, or you can fully hydrogenate to here, and this is done just by a metal like zinc and a strong acid like trifluoroacetic acid. So making this, from that you can make anything you want. And that is what we have done, and so then we can start studying more molecules. We have also done the X-rays, anything, and what it shows is that, as you expect, once you start hydrogenating one of the rings, this ring is no longer flat. It's no longer aromatic. So it buckles up. And on top of that, of course, now the methyl group can rotate away from the plane of the carbon-sulfur. And that, of course, is the trick. The trick is that once you do the hydrogenation, this methyl group here is coming out of the plane where the sulfur was and the other methyl. And here you see a more space-filling model. When you do a hydrogenation of both rings, of course, it becomes more easier to desulfurize. I've indicated, by the way, for the connoisseurs that each ring now has 3 prochiral atoms, so there are, in this case, 20 isomers. In the former example, there were 4 isomers, and we have seen them. So there's a lot of organic chemistry in such very simple molecules. Now, once you have the tetrahydro, you can start with the tetrahydro, and now you can do all the kinetics of that, and we did. The surprise was it doesn't go back. It doesn't dehydrogenate to the dimethyl dibenzothiophene over a moly catalyst or over a nickel moly catalyst. When you do it over a metal, it does. But over the classic catalyst, it doesn't. It goes very quickly to the hexahydro. You see the tetrahydro go down and the hexahydro come up. When I start at the hexahydro, you see that they are almost in equilibrium, because now the hexahydro shoots down and the tetrahydro comes up, and they're almost giving you the final result, like this is a very fast equilibrium. Now, by looking at the selectivity plot, as engineers know, you can say something about which of the product is primary and which is secondary. If you have an intercept with the vertical axis, selectivity axis, which is non-zero, then you have a primary product. If it's 0, you have a secondary or higher order product. So this is what we did. And this brought us to this scheme, which is a couple of man-years work. You see that the first step, if you don't have methyl groups, this is reasonably fast. I've indicated in the thickness of the arrow how easy it is. This step is 3 times more difficult, more slow. Once you're here, this is sort of in equilibrium, as you see, very fast reaction back and forth. You still have, this is without the presence of H2S, a reasonably fast desulfurization, both from here as well as from here. That's a surprise. The literature had always assumed, not knowing, not having been able to start here or here, had always assumed that it reacts through here and never through here. The surprise is this is even faster. So this is also possible. Actually, it shouldn't have been a surprise. If we can break an aromatic CS bond, why shouldn't we be able to make a vinyl type of a CS bond? That should be weaker. Now this one is an aliphatic CS bond, and apparently it is slower. That's a surprise. I'll come back to it. Now you add H2S, and what you see is that the hydrogenation route is exactly equally fast. You have lost this here. So the hydrogenation with the H2S over moly is equally fast. This has not been recognized by many in the literature, that the hydrogenation isn't influenced much by H2S. It's the desulfurization. So apparently, and that was already in the literature, we do need vacancies there so that the sulfur from the molecule can stick its nose into the vacancy, link to the molybdenum or to the nickel or to the cobalt and do the job. Now when we go to nickel moly, now with H2S, you see why nickel moly is the preferred catalyst over the moly, why nickel is used as a promoter. You see that first of all the hydrogenation route is very nice, but now even in the presence of H2S, we added 35 kilopascal, you still have a high rate or reasonably high rate of desulfurization. So this is the answer. That's why you use either cobalt or nickel. And the question, why is that? Do we understand that? And the answer is, by now, in the last decade, we have started to understand. I will give you some results from theory, not from our group. I'll mention the groups in a minute. Originally, it was believed, here again you have your MOS2 slab, which is standing up. And there are two sides of it. The top part is, you see again those molybdenum atoms, which I showed you some 10 minutes ago or so. Of course, there is also a bottom of this. Now, where is the mouse again? Here, this side, and I can turn it top down, and then you have these atoms here. This is what we call the sulfur edge. You see the sulfur at the outside and the molybdenum below it, actually totally covered by the sulfur. So you don't expect this sulfur edge to be active catalytically. And originally, more than 10 years ago, this so-called molybdenum edge was supposed to be the catalytic active edge. However, the density functional theory from many groups has shown that this, of course, is a very unstable state. Molybdenum, like any metal, doesn't want to be so naked as here in the left-hand side. So what you get is a reconstruction. Half of the sulfurs here, each for every molybdenum, go to the other side, as it were, and cover it. And now the molybdenum here is six-fold coordinate in a trigonal prism way, not in an octahedral way, in a trigonal prismatic way, but is fully coordinated. So now the edge, which originally was supposed to be catalytically active, is now, by DFT standards, is totally inactive. And now the activity is supposed to come from the edge, which originally, before we even thought about reconstruction, is now half open. And now your molybdenum here is tetrahedrally surrounded, and you can have 1, 2 more ligands there, and you can do the job. You can desulfurize. What about cobalt and molybdenum, cobalt and nickel as promoters? They are known to promote the activity of molybdenum sulfide by a factor like 3, 4, 5, up to 10, depending on conditions. So they're very good for you. We know since the work of the group in the Topso lab, led by Henrik Topso, but there are many others who did a lot of work there, that they are replacing, as it were, molybdenum atoms, and they're at the edge. So, and now by the work in the past decade on the DFT, we have an indication where they really are. And here you see the cobalt moly, and now here you have the reconstructed molybdenum edge, which is now, as I already said, is fully covered. But now the cobalt is replacing the molybdenum atoms at the sulfur edge. Now, as an inorganic chemist, you could have predicted this. Of course, it's in hindsight always easy to say denigrating things about DFT. I don't want to do that, but let's say if you are an inorganic chemist, if you had to predict where is the cobalt going, is it going to an octahedral site or is it going to a tetrahedral site with sulfur as ligand? The answer is, of course, it goes tetrahedral. So it makes good sense. And where is the nickel going? Well, the nickel is not, as a nickel 2+ like, going to a tetrahedral site because you have Jan Teller problems. So it goes to an octahedral site, but it lets go one sulfur, and you are getting a square planar situation. It's like here taking off the sulfurs, replacing the blue balls by green nickels, and now the nickel sinks into the layer, and you get a square planar array. And this is what nickel likes very much. So you see that the molybdenum is in these sites, the cobalt is in molybdenum sites, and the nickel is in different sites. So all three catalysts actually can have a different activity. So it's not a surprise that the nickel and the cobalt are doing a good job, and especially the nickel is very good in hydrogenation, as long as you don't have too much H2S. Because of course, if you put too much H2S on it, then you are going to cover the green balls, and then there is no place for your sulfur-containing molecules anymore. Now here is a top-down picture. This is the work of the Fleming-Besenbacher group. They did STM on these systems. And before that, I'll show you the DFT people who did all the calculations. It started again in Denmark with Jens Norskov, and then pretty soon thereafter, the French had a very large consortium of groups. The IFP group, led by Hervé Toulois and Pascal Rebaud and others, then the group in Lille, and again the Toulois group, and then also finally in the United States. So actually this was Canada. This was Edmonton, where Alan Nelson did calculations. So over the past year, these calculations have learned us a lot about things which are very difficult to approach from experimental side. Now, going back to the Besenbacher paper again, what I want to show here is a STM picture in color of the MOS2 from the top. And what you see is right behind the edges, there are sulfurs which are having a high color, and that means high electron density. So the suggestion is that just right behind the outward sulfurs, they call it the brim edge, you have electron density as if you have a one-dimensional metal like in a circle going around this particle. And this explains why MOS2 type of materials, although band gap type of arguments and insulated type of arguments will not predict that it is a metallic-like system, you can see here, and then you go to theory again, you can predict, and now you can see experimentally here, that is a one-dimensional type of a metal, which is not a very good metal, but it is a metal. And that explains why it can split hydrogen and why it can do its job. Of course, we would have liked to have a better metal. But because we are making H2S out of a sulfur-containing molecule, and because H2S is very strongly binding to any metal will turn into a sulfide anyway. So then you must start directly with a sulfide, and then MOS2 is one of the best. And that's why it's taken in the industry. Now finally, in 1 or 2 minutes, I already promised you to say something about which bond is really broken. And we have done DFT calculations on this model molecule, which is like dibenzothiophene, although one ring is taken away. So 4 carbon atoms are taken away. So this is like hexahydrodibenzothiophene. And the question is this red bond broken or is the blue bond broken? I would say that all of my colleagues, me included, 2 years ago would have said, of course the blue bond. We know that a CS bond, where the carbon is aliphatic, is much weaker than an aromatic one. Look at the infrared, look at anything, thermochemistry, anything. But that is like playing chess and only thinking one move ahead. And as we know in bridge and in chess, you better think a few moves ahead. So think about the product. The product has, in that position where the sulfur was, has a hydrogen. So the product, CH bond, is also stronger for the aromatic case than for the aliphatic case. So you are replacing a strong bond by a strong bond and a weak bond by a weak bond. And the question is, which is the winner? So actually, if you don't do the theory, it's difficult to predict. So we did a DFT calculation. We took a model. And here in the middle, you see is a molybdenum atom, and it has one vacancy. So we can dock here a sulfur-containing molecule. We now have also done it with nickel, and the outcome is the same. I'll just show you only the molybdenum. So here you see your benzthiophene molecule coming, goes down, and now you can either have it bonded, the aromatic bond breaking, so that means you have the aliphatic still here, or you do it the other way. And when you look at the energetics, you see that the activation energy, we did the full calculation, is lower when you break the aromatic bond. So it's this compensation effect, which apparently is the CH bond is helping you to win. Well, if you very carefully look at the calculation, there is a little bit more than that. There's also a stereo factor. It's easier to break that bond also because of stereo. Now with that, I have come almost to the end. I just want to mention a few other techniques, just mention them, which are at the moment heavily studied by many of my colleagues in the world, also by industry, but they definitely haven't made it yet. Of course, you hear colleagues claim that this is fantastic, but it still has to go to pilot plants and whatever have you. And so it will not be used in the coming few years, but it might be used in the future. I don't think it will be used in the coming 5 to 10 years in the Western countries. And the reason is that the refineries in the West, they have already made a decision to stay at the classic hydrodesulfurization route and found solutions. Whereas in countries where you have to build new refineries almost every month, there's plenty of opportunity to go the grassroots route, which there isn't in established, mature societies like in the West. So I think that when we will see this process to come into operation, it will be, I think, in Asia. So my conclusions were that as far as the mechanism is concerned, the molybdenum disulfide with its promoter is more like a metal. Now, in the beginning, I posed a question, and I've talked a lot about the drivers of this industry and of this science and the science. And a good story is like a circle, it must make full loop. So I have to come back to my question. What about it? Because otherwise I leave you with this question. You still don't know if you are allowed to drive a car this evening or tomorrow. So does Catalysis allow driving a car as well as having clean air? And you see what the problem is. If you drive a car, there is an oil industry behind it. We have to remove the sulfur to have clean air. So there's two problems. Legislation, but legislation is you, and especially those countries that don't have the right legislation yet. Make sure you get it. Then you will have clean air. The industry is more or less capable of doing it, so the industry will deliver it for you. Of course, you as a client have to pay the bill. Nothing is for free. You will not get the gasoline at the same old price then. The other thing is, of course, well, another way, put it another way, can we drive a car and have clean air? The other thing is, shouldn't we be driving less? Shouldn't we be driving more efficient cars? If you have followed the car industry and the oil industry over the years, and I've seen an article recently about the United States, over the past 30 years, 3 decades, the car industry and the oil industry made everything more efficient. Why aren't we getting more miles to the gallon? Why aren't we getting more kilometers to the liter? Because we love luxury. We have heavier cars, we have more equipment on board, we are driving more heavy, nice, big cars, so we have wasted the improvement, which definitely was there over the past 30 years, into the direction of luxury. And we love it. You go to Asian countries, I won't mention an example because it's true for all of them. And many of my colleagues there, they drive bigger cars than we do in Western Europe. And they have less children. So, but it's fine. Of course, I understand that everyone wants to drive a nice car, and that's beautiful. But the end of the bottom line is, will there be oil enough? I haven't addressed that question. I will not. The other question is, what will it mean for the amount of sulfur, and so on and so on. And he has taken away my bottom line. What do I do here? What does it mean? I have 1 slide, 2 slides to go. Okay, so the bottom line is, can we drive and have clean air? I'm trying to, I don't see it here on the screen yet, so. Can you take the next one? Because I can't. Yes, we can. Oh, so I'm going too quickly. Can I go back? Oh, no. What are you doing now? No. Go back. Can we go back? Because I can't. I don't know how to do that here. Well, okay, forget it. There were many students who did all the work. I had several students from my own group in Switzerland. Yeah, where are we? Yes. Okay, take this one. Yes, here they are. Okay, so Fabio Rota, Marina Igorova, Theodora Todorova, they were PhD students from my Swiss group, and Yonggang Zhao, you will recognize he comes from China, and Pavel Kukula, he came from the Czech Republic, Adelina Reutlisberger came from Switzerland, Thomas Weber, who's now with Shell, was involved in many things, amongst others the DFT calculation. Then I had postdocs like my colleague Wang Anje from Dalian and his co-worker Li Xiang. And recently I had two postdocs, Huamin Wang and Yin-Yong Sun, and they did all the work. Thank you very much for your attention.
Well, thank you very much indeed for a very nice presentation, a nice overview of the importance, the complexity and the difficulty of hydrotreating and the work that you've presented on the use of model compounds and kinetics actually, which in catalysis is sometimes forgotten about, is very revealing indeed, and we thank you for that. I'm sure everyone will join me for two reasons in thanking you. One is that we can still drive our cars, and the other is to thank you very much for an excellent lecture.
One moment, ladies and gentlemen. The organizing committee prepared a small present for speakers. I will pass it to him. Slide, please.
Okay, there was just one more slide for the benefit of speakers from tomorrow. But if the slide doesn't appear, the message is, can you please make sure that you have your presentations, the PowerPoint presentations, whatever, available 6 hours at least before the time of your presentation? Okay. Okay, fine. The next event, as everyone now knows, of course, is the reception.
That's already to reception.
And so I, on behalf of the local organizers, invite you to join me at the reception.